So, okay, thank you, Arun. So, in today's lecture, uh, I'm going to discuss about the lens defect. What are the different type of defects which are coming due to uh, aberrations, and what are different filters we use in order to enhance the imaging capabilities, and then I'll be discussing about the light microscope and the different parameters involved in it, and I'll be discussing those, and then I'll be discussing about bright field imaging, then opaque specimen illumination, opaque stop microscopy, why we need this, and how it is different from phase contrast microscopy. Then I'll be discussing about dark field microscopy, and at last I'll be discussing about polarization microscopy, and then I will discuss the assignments, practice assignments which are given. So to start with, lenses defect. So there are basically three types of aberrations which we find in lenses defect. One, one is coming because of on axis, one because of off axis, and one because of distortion. So in on axis aberration, we will discuss chromatic and spherical aberration. Most of the aberration which we'll talk about, all will be in the light source will be monochromatic, so it won't be a problem. But while considering the chromatic aberration, it contains light having different wavelength. So first one, chromatic aberration. So this chromatic aberration occurs because the lens refracts light differently. So depending upon the wavelength, we may say, as we know, different, like blue light, red light, they have different wavelength. So blue light will bend inward toward the optic axis more, and the red light will bend away from the optic axis. So this we say optic axis. So when white light is shown on the lens, then as different lights have different wavelength, they will have different point of focus. Okay. So the higher the wavelength, they will be focused at a larger distance than the lower wavelength light color. So how this can be resolved? So the solution is making compound lenses of glasses having different color dispersion. This is one of the solution. And another solution which Sir has also mentioned in his slide, that is by taking different glass types. Let's say we take two glass types, crown and flint glass. They are paired together. They are paired together to make, this is called a achromatic doublet lens. This helps in focusing blue and red wavelength in the same image plane. Blue and red wavelength, same image plane. Now the next aberration is spherical aberration. So in spherical aberration, as most of the lenses which we consider are spherical in nature, so it's very difficult to avoid this one. So because of the spherical nature, at different planes of the lens, like away from the optic axis, wherever the light will be passing through the lenses, they are going to have different focus point accordingly. Okay, so spherical, so they have different focuses because of different width of the lenses. Okay, so this is a very common problem and it's very difficult to curve this, and this can easily be curved by using both converging and diverging lenses. This is one of the solution, and there's another way that is mentioned by sir only. So but there is another way it can be resolved is by using special type of objective lenses where they have adjustable correction collars. So next is coma aberration. These first two aberrations were talked about. First one was on axis. The spherical aberration is also on axis aberration. Now whatever aberration I will talk about, those will be off axis aberration, and those are coma and astigmatism. So first one, coma. This cause, what it does is causes point object to look as comets. Like if focusing the light from the distance, so it will be having a focus spot with a tail, and it affect the image of points located off the optical axis. So this happens because the lights are falling obliquely. Okay, so when the rays passes through the edges of the lenses, they are focused far away from the optical axis, and which are passing closer to the optical axis passes through the center of the lenses, and this helps in making this comet like shape. So for different lenses it has different effect, so it is more greater for lenses with wider aperture. And how we can correct it? Like we can make the lenses in such a manner that our we will make our lens in such a manner that our sin I by sin r is a constant. This is one of the way we can curve it that this is construction, in terms of construction of the lenses. So but there's also other way we can also curve it by accommodating the diameter of object field for a given objective. Accommodating diameter of object field for a given objective. So next off-axis aberration is astigmatism. This is a very common problem. The people having cylindrical lens, the people who have this problem, they often use cylindrical lenses, which you guys might have known or might have seen. Someone uses glasses. So here what happens is it has two planes to work with. One is sagittal focal plane and one is sagittal plane and one is tangential plane. So because of, again as I told, this is off axis. So after reflection through the lenses, okay, they will be again focused at different points. And they will have different patterns formed. And these patterns are called airy diffraction patterns. So here this problem increases with increasing displacement of object from optic axis. When this is our optic axis, we move away from the optic axis, like the reflection will be having here or from here, this problem start to increase. Like let's say we expect a circular kind of object, then it will not be circular anymore, because of distortion in different planar axes, maybe on x plane or maybe y plane or maybe x plane. It will look as elliptical. The image will look elliptical rather than circular. If it will look circular, then it is fine. Otherwise it is having this problem. And as I've already told you, like we use cylindrical lenses in our eye to curve this, or normally stigmata is used to solve this problem. Then curvature of field, which is again another off-axis aberration. This happens when the image plane is not flat. So different zone of image can be we can bring different zone of image into focus, but the whole area of our image will not be focused. Let's say this is aperture, at certain point we will focus it, then periphery point will not be focused. The more we will focus the other point, this point will defocus. This point will come into focus, and its periphery point will again defocus. But this happens because all the points where we want to focus are not in a single plane. So this can be corrected by designing our objective lenses. And sometimes we can also design our eyepiece in such a manner we can diminish it. It's very difficult to resolve this problem totally. We can diminish its effect to a larger extent. Then last one is the distortion. This causes the focus position of object image to shift laterally. As we have seen, like this can be in horizontal plane or vertical plane. So as we move away from the optic axis, the more we go away from the optic axis, the more this distortion creeps in. So why this distortion is happening? It's because of the nonlinear magnification. So there are, as we know, there are two type of distortion happens. One is pincushion and another one is barrel. So depending on what gradient it is there, whether it is increasing or decreasing, we have either pin cushion or barrel. So here it will, the image will kind of look like this, and for barrel class it will look like a barrel. That's why it is called barrel distortion. Next, we'll go to the characteristic of objective lenses. Like, there are different kind of objective lenses used to eliminate these problems. So what are the different type of objective lenses are there? Different types of objective lenses. One is achromat. What are they? These are red, blue corrected. This give very nice performance for monochromatic light. And good for low magnification, that is 30-40x or lower. So when we say this blue or red corrected, what are the wavelengths we normally consider? For red, let's say 6556 nanometer, and for blue it is around 486 nanometer. This you can remember. The next kind of objective lens is fluorite, or this is called uh, semi-achromatic. Semi-apochromat objective lenses. This contains elements of like fluorite or CaF2, or yeah, this kind of things. This kind of materials, these are made of this kind of materials. And why we use this? These are for correction for color dispersion, and curvature of field can easily be corrected using this kind of objectives. Then third one is apochromats. These apochromats can be used for spherical aberration at green and blue wavelength, and these are these are the most costliest one. So yeah, these are the different kind of objective one used uh, in a light microscope. So the next, so like we use different kind of objectives, we also have different kind of uh, eyepieces too. So this is, there are basically two kind of eyepieces we can have. One is field lenses and another one is eye lenses. So their main objective is, the main what they do, like the, as we know, they help in magnifying primary image, helps in magnification of primary image, with respect to that they also helps in correcting the residual chromatic aberration. Another point, they also help in flattening the field of view, and also helps in correcting astigmatism. So these are the two parts which are more most important in light microscope. One is objective, another is eyepiece. Now going to the filters, we use to, you know, getting desirable light which we want for, you know, getting better images. There are three type of filters which mostly people use. Short pass, as the name suggests, it only allows the shorter wavelength. Then our long pass filter allows longer wavelength light, and band pass filter. Like in electronics, here in light also, there is a proper filters can be used to allow certain kind of wavelength of light desirable to us, allows certain band of wavelength. So the question comes, why we need these filters? We need this filter to adjust the intensity and wavelength of illumination, because as we know, whatever image you will get, that totally depends on the what kind of light is coming through. That's why earlier also it has been discussed, like with numerical aperture we use the a different kind of materials, like different kind of liquids, to enhance the light capturing uh, property of the microscope, so that it will give us better resolution. So while discussing this filter, there's a very important concept called interference filter. This helps in this allows very steeper wavelengths to pass through. They have very steeper cut in and cut-off transmission. It compare with respect to what? With respect to colored glass filters. So that's why it is very helpful in fluorescence microscopy. Here we did sharply defined bandwidths. So what are these interference filters? They are optically planar sheets of glass coated with some dielectric in multiple layers, and those layers can be lambda by 2 or lambda by 4, and they help in blocking the transmission of specific wavelengths selectively, and then uh, they go through constructive and destructive interference, and we get the aspired result. Next important concept, we'll look for before going to the bright illumination is, we'll talk about a little bit about light microscopy and what are the different parameters needed for light microscopy. So as we know, like very important uh, uh, components of light microscopy are objective lenses, which I have already discussed, then eyepiece. So then there is another material used called condenser, which helps in better magnify the image, and we can get a better result from our microscope. But up to 25x magnification, we don't require this condenser for getting better image. We don't need condenser. Objective itself can work properly. Objective itself will give us better result. So, but again, as I've told, like there are different parameters. One, these three components, and what numerical aperture. For better optical microscopic image, we need better illumination, and for better illumination, we look forward for numerical aperture. So, and another one is reflectivity. So, for best optical image, we need numerical aperture of condenser to be equal to numerical aperture of objective. And if we have better numerical aperture also, that also helps in giving us better illumination, and hence it gives us better reflectivity. Better numerical aperture, better illumination, optimum reflectivity. So like in light microscope, the images which we get are kind of like for higher magnification it is obstructed, so we kind of need the light to be coming through oblique angles. So in order to curb this issue, one need this so that's why this oblique angle is very important uh, in our light microscope. So along with this numerical aperture, we also have to take care of oblique angle. So what are the different uh, parameters we need to consider in light microscope? One is analyzer, like what kind of light is falling and how we are analyzing it. Reflectivity, numerical aperture, elimination of opaque specimen, oblique illumination, these are kind of some important parameter one needs to look forward while considering this light microscope. Then after that, people look for bright field imaging and dark field imaging are done in this light microscope, which I will discuss in further slides. So next, like in light microscope, what kind of imaging is possible. One is bright field imaging, and another one is dark field imaging. Here in bright field imaging, light is reflected back towards the objective from reflective surfaces, cause, causing them to appear as bright. And in dark field imaging, it is totally opposite of that. Like the grain boundaries which are present in the material, they appear as to be bright, and the background is totally dark. Here background is bright and the object which we need are sort of having different contrast. Here background is dark. So mostly we do our imaging in these two kind of imaging processes. Then next, if it is not possible to use this bright field imaging, so how image can be processed? So there are different mechanism employed to resolve those issues, and those can be resolved by either phase contrast or polarization microscopy, and there are other methods to curb the limitation of this bright field imaging. So why we need different microscopy technique other than this bright field imaging, dark field imaging? Because some materials do not exhibit, some materials do not exhibit contrast in bright field illumination. So here, to curb this problem, we can use phase contrast technique, where phase change can easily be detected. And how this phase change helps in detection of the object? Here, difference in phase of object is translated to difference in amplitude in image. It is translated to differences in amplitude of image. To understand this phase contrast, we need to know like what are these amplitude object or phase object. So to understand this phase contrast, we have to look for effect of amplitude and phase object. So let's say we have a reference wave. So let's say we have an amplitude object, that is, its properties like that it kind of changes the amplitude of the given waveform. And for phase object, what it does is it changes the phase of the reference wave. So here amplitude can be reduced or increased. Similarly here phase can be uh, decreased or increased, which we also call retarded or succeeded. Which we also call when in waveform we call lagging and succeeding. So what it will make to the transmitted light, let's say we have a phase object. Okay, so let's say we have incident transmitted light. So when it passes through the phase object, then the wavefront will change. Now next, to understand this bright field illumination, we need to know certain kind of terminologies in optics. Those are like what are S wave, what are D waves, what are P waves. So in bright field illumination, we have different kind of waves. One is S wave, one is D wave, and another one is P wave. This S wave is also called a non-interacting wave. D wave is called diffracted wave, and this P wave is called particle wave. And there is a relation defined for these three waves, and it goes by P is equals to D plus S. So let's say in terms of wave, let's say this one depicts our S wave, this one having different phase depicts P wave, and this one depicts D wave. D wave, this is P wave, this is S wave. This S and P waves, what they do, S and P waves, their relative intensity determines the visual contrast. And this D wave is not directly seen in the image. So the amplitude of each of the wave, they represent the sum of electric field wave vectors of photon which we are emanating over our object, and we are getting the image out of it. So here we will say the D wave is having lower in amplitude than S wave, because there are less D wave photons than there are S wave photons at the image point. So here we can see the D wave is retarded from S wave by lambda by 4. Let's say this is our wave. This is our wave, and it is having wavelength of lambda. Then this D wave is retarded from S wave by a factor lambda by 4. And this phase shift which is occurring in diffracted wave, we can correlate this with scattering and diffraction. This phase shift can be correlated to diffraction or scattering. This P wave resulting from the interference between D and S wave is retarded relative to the S wave, as we can see here, by only a small amount here, by only a small amount, that is lambda by 20, and has amplitude kind of similar to that of S wave. So as this S and P have similar kind of amplitude, in light microscopy there will be no contrast, and this object, we can say this object seems to be invisible, as there is no difference in amplitude of P and S wave. So how in this phase contrast, like how it is different from light microscopy which we use, they are using one phase plate. Like from light microscopy, the bright field imaging which we do, how this phase contrast is different from this bright field imaging. We are using additional phase plate in our optical system. Because of that we are getting this difference. How this phase plate is helping in getting the phase contrast? This phase plate is etching out certain parts. So that the path taken by ray is reduced at certain portion where it is etched, and it will be same at the other portion where the light ray will take more time to travel, and hence it recedes the other ray. Like let's say here we will do the etching. If light is coming through here and through here, the light will take lesser time through this part than this part. So because of this time difference, we are getting those phase difference. Like we can say the wave is lagging behind here with respect to this path. So we are getting a contrast in our imaging process. So this is how the phase contrast is different from bright field imaging. Only by using one phase plate we can convert our light microscopy imaging into a phase contrast imaging. So next we have polarization microscopy, where again we do get different kind of imaging. from different by exploiting the different phenomena of light. So for this microscopy to use, the object which we are going to take has to be polarizable in nature. Object has to be polarizable, and they should have proper ordering and directionality. So here what is happening to the wave? Here the perturbation to wave, or whatever polarized light we are employing, they are perturbing from the aligned molecules. So an object result in phase retardation between the sampling beams, which are in turn allows the interference of those waves, and this changes the amplitude in the image plane. So here image formation is dependent on diffraction, interference, as well as the ordering. So why we need this polarization microscopy? We, so to analyze transparent samples. Because it's very difficult to get imaging of transparent sample using bright field imaging or phase contrast. So this microscopy involves different components, namely polarizer, analyzer, which are main components here. What this polarizer do? They help in producing polarized light. And a common example is Polaroids. Next, analyzer, which is also a kind of polarizer, but the difference is they help in determining the plane of vibration. So what all other concepts needed for this polarization microscopy is, the next concept is called double refraction. Like many many crystals, or rather we say like a transparent crystal, so this kind of uh, phenomena like quartz, calcite, rutile, and so this kind of phenomena, why they this so this kind of phenomena? Because they are optically anisotropic. they show this phenomena because of optical anisotropy. So this phenomena is also termed as birefringence. What does this mean? Or why this phenomena occurs? Because of the atomic arrangement. It occurs because the atomic arrangement causes direction dependent differences in refractive index, and because of this we get two type of rays called ordinary rays and extraordinary rays. So this ordinary rays, or which is called O ray, OR, ER, these ordinary rays, they follow the laws of normal refraction, but extraordinary rays do not follow these laws of refraction. They travel along different paths. And after splitting, this ordinary ray and extraordinary ray that emerge, they are mutually perpendicular to each other, and they are linearly polarized too. So this birefringence it also refers to a measurable quantity that is experienced by this ordinary and extraordinary rays. Like we can denote this birefringence as the difference of the refractive index of extraordinary and ordinary rays. So that is depending upon the values of Ne and N0, this birefringes can be positive or negative. And these terms can also be related to terminology called relative retardation, which has an analogy with optical path difference. Relative retardation, gamma is denoted by Ne minus N0 by into the thickness of the material. This can be correlated with the optical path length. So this double refraction or birefringence, these are property of polarizers which we use in the microscope. The property of polarizer that we use in microscope as well as material which we use. This all phenomena will be used in fluorescence polarization microscopy. So as we know, we will take two polarizers and we can put it in front of each other and we'll rotate it. There, by doing that, we can control what amount of wavefront we need to get, and that phenomena is also the amplitude of the wave which we'll get can be given by very famous known law called Malus law. From there we can correlate and can calculate the amplitude of the wave whatever we'll get. So these are the concepts which have been taught. In this week of lecture. Now let's come to the questions. First, in light microscope, during bright field illumination mode, the region which appears bright are from which rays? Low reflectivity rays, high reflectivity rays, independent of reflectivity. As I have already told you, in light microscopy, reflectivity plays a vital role. So here during bright field illumination mode, the region which appear bright are from high reflective rays. But in the case of dark field illumination, it will be the reverse case. Very important parameter in light microscopy. So with increase in illumination, we have higher reflectivity. So up to total magnification of what, this condenser is not required in light microscopy. As I have told you, it's 25x magnification. Below that we don't require any condenser. Objective lens itself will work and we can get a good magnification, and above 25x we do require a condenser lens. Which of the following lens defects is an on-axis aberration? Coma, it's an off-axis aberration. Astigmatism, this is also an off-axis aberration. Chromatic, this is a on-axis aberration. And how this can be eliminated? By taking a monochromatic light. This can easily be eliminated because this problem comes because of light having different components with different wavelength. And how this coma can be eliminated? This is by constructing a lens according to our choice. And this astigmatism, this by using stigmator or cylindrical lenses, we can easily curb this problem. Next, the overall resolving power of optical microscope depends on numerical aperture of objective and illuminating system, numerical aperture of condenser and objective, numerical aperture of condenser and illuminating system. Just so as I have already told you, the illuminating system and the what type of objective which we are using matters a lot. And with numerical aperture, like we use different kind of liquid to increase the amount of light one microscope can acquire, and accordingly it enhances the resolution of the microscope. So the correct answer will be numerical aperture of objective and illuminating system. So in a light microscope, replacing green light with red one will dash the minimum detectable distance. So as we know, green light is having lower wavelength with respect to the red one. So if we replace the green light with red one, the minimum detectable distance will increase. In polarization microscope, the compensator is used for specific phase shift in ordinary ray, specific phase shift in extraordinary ray, specific phase shift between ordinary and extraordinary. The compensator is used for both ordinary and extraordinary ray, so the answer will be specific shift between ordinary and extraordinary. The polarizer and analyzer of a polarization microscope are made of which material? So it has to be anisotropic, as I have already discussed. If the material is anisotropic, then only the material is polarizable and we can use this technique. The opaque stop microscopy is also known as the name suggests, it is opaque, so it has to be dark field microscopy, so it is also known as sensitive dark field microscopy. In an optical microscope, the filters are used to adjust frequency of illumination, intensity of illumination, wavelength of illumination, both intensity and wavelength. Filters are used to control both intensity and wavelength. So the answer will be both intensity and wavelength. In phase contrast microscopy, the amplitude of the light wave corresponds to brightness of the reflected rays, phase shift introduced, or difference in the optical path lengths between specimen ray and reference ray, difference between the crest and trough of the wave. So here the amplitude of light wave corresponds to the difference in the optical path lengths between specimen ray and the reference ray. As I've already explained, like we in phase contrast, we take a reference ray, and with respect to that we have two things, amplitude object and a phase object. The amplitude object, what it does, amplitude object changes the amplitude of the wave which the reference wave have, and the phase object changes the phase of the reference ray. So here the amplitude of the light wave corresponds to the difference in the optical path lengths between specimen ray and the reference ray should be the answer. Illuminating source in fluorescence light microscopy, it is ultraviolet. Because in this microscopy it will not be able to apprehend any wavelength corresponding to visible or IR. So it has to be lower wavelength and high frequency. It requires these two specification for the source. So from the following statement, which of the combination is true or false? So coma is the off-axis defect, that is correct, that makes the image to be blurred disc or lens. This is incorrect because the off-axis defect that makes blurred disc or lines, this correspond to astigmatism. Rays from the corner of the lens and from the center of the lens are not in focus. This effect is attributed to spherical aberration. That's correct. The rays of different colors fail to converge at a point after going through a converging lens. This effect is attributed to chromatic aberration. That is correct. The greater the aperture of the lens, less severe will be the spherical aberration. That is incorrect. The severity will increase. So false, true, true, false. So the answer will be C. Which of the two optical microscope components combine to give a magnified view of a small specimen? Two optical microscope component. For magnification, we need objective with eyepiece. So this objective and ocular lenses are main lenses. This ocular lens is also called eyepiece lenses. An optical microscope is used to examine a metallic sample that has been properly polished and etched. Which of the following parameters cannot be qualitatively analyzed? Grain boundary, it can easily be analyzed. Grain size can also be analyzed. It's the grain orientation which cannot be analyzed. So this is the answer. So this is it for the week 2. So whoever have any question can ask, or we may end the session. I'll be here for around 30 minutes, so you may ask anything you want. So as we know,
Here in polarization microscopy, and another thing to keep in mind are the concept of polarizer and analyzer. Along with that, we need to know a little bit about birefringent specimen and how the ordinary ray and extraordinary ray are coming and helpful to us.
we can get elliptically polarized light, right? So here, birefringent specimen, what it does, it splits rays of incident light into ordinary ray or extraordinary ray. So we may say there is a propagation vector. Ordinary ray will lie in one plane and extraordinary ray will lie perpendicular to it. So here we can say our ordinary ray or extraordinary ray which is formed, they compromise each ray or wave bundle as they become mutually shifted in phase because of different refractive index each wave experience when they pass through the specimen. So here as ordinary ray and extraordinary ray, they are mutually perpendicular to plane and also to each other. They cannot interfere. So how does this point helps is in polarization microscopy, as the interference is required to generate a contrast image, convenience for describing the behavior of the superimposed wave pair, we may add the two waves together to form a single resultant ray. The mutual perpendicular orientation of two electric field vectors and phase difference between the two rays result in a three-dimensional waveform called elliptically polarized light. and waves resulting from this combination of superimposed ordinary or extraordinary ray they have elliptical, spherical or planar waveform depending upon relative phase shift between two rays. So it can be 0 or m lambda depending, like any integer multiple of lambda. This is the rotation of polarizer with respect to the analyzer, or it can be lambda by 8 or more, lambda by 4 or it can be lambda by 2, and it will have only one direction of polarization, so on and so forth. So if the polarization and analyzer are totally in opposite direction, then the total light passing through them can cancel out and we'll get no light out of it.